Hello everyone, my name is Zhenyou from KIT, and our contribution or our main task in the image project, we are dealing with the cathode. So we are aiming at high capacity and long cycle life magnesium cathode, and we are also involved in the development of the magnesium electrolyte. But we are mainly focused on this chlorine-free electrolyte system. And that's why today I just want to show you our kind of compatibility test of the non-corrosive electrolyte with different magnesium cathode materials. So to start my talk, I would like to give a brief introduction of the development of magnesium electrolyte. And I think some of the points has already been given by Professor Albach in the previous talk. So basically, if we change from the lithium system to the magnesium system, if both cases we use the metallic anode, we will face definitely different issues. For example, when the electrolyte that has been used in the lithium batteries, the carbonate, for example, it's not compatible with magnesium anode. So in case of lithium, we always have like the ion conductive layer on the lithium surface that kind of protect the lithium anode, so that we could have continuous cycling. But in case of magnesium, the reaction between magnesium and the solvent will result in a passivation layer that's blocking further ion mobility. Also, another point I want to given is that there will be native oxide layer on magnesium surface. So we need some kind of activation so that we have fresh magnesium towards the electrolyte. So our goal is to achieve this reversible plating and stripping of magnesium. And I mean, the first generation of magnesium battery that could deal with this problem or realize the reversible magnesium stripping and plating is to apply a Grignard-based electrolyte. We know that Grignard agent is reactive, and they could condition in the moistures and also some oxidant species in the electrolyte solution, and could also somehow clean the magnesium surface. And with the addition of the chlorine species, we have the well-known APC electrolyte reported by Professor Albach's group. And definitely with the addition of chlorine, we have an extended like electrochemical window, and we also have better ionic conductivity. But the limit is still like in the APC case, we have a relatively narrow electrochemical window. And this kind of limit us to further develop a high, or just to investigate the magnesium storage in a high voltage cathode. Also, the nucleophilic nature of the electrolyte makes it incompatible with sulfur cathode and also with the organic cathode. And that's why several non-nucleophilic electrolyte has been developed. For example, the magnesium TFSI with the magnesium chloride case, as highlighted by Professor Albach, and also the magnesium HMDS electrolyte. This is also in combination with the metallic chloride. So in this case, we could see that from the CV, we have like extended oxidation stability for up to 3.5 volts, which is much improved than the APC case. And also, as demonstrated in the magnesium sulfur cell, it's compatible with the electrophilic cathode materials. So in fact, with this non-electrophilic electrolyte, we already investigate the magnesium storage capability in a broad range of cathode materials, but then there's still the remaining issue, the chlorine. So we know that there are, the chlorine has multifunctions in the system, but the corrosion is still like the issue there. So this is especially the case for oxide, for example, the transition metal oxide, which is still the choice of the market, I would say, in the case of lithium-ion batteries. And also, it's a promising high voltage cathode material for magnesium batteries. So you have to somehow find a way to develop an electrolyte that is also at least compatible with this high voltage cathode. Also, the chlorine or the corrosive issue makes us to think about, at least we have to make special design, anti-corrosive design in the cell manufacturing, for example. This is will add additional cost and efforts. And on the other hand, we also have a complicated solution environment with dynamic equilibrium in the chlorine-based electrolyte. As shown before, we have a couple of these magnesium chloride cluster species, and this monocharge carrier has a possibility even to intercalate into the system as a whole rather than the double charge carrier. And as reported before, the magnesium chloride storage, if we have this scenario, then we might need more electrolyte if we want to achieve the same specific capacity as in case of this magnesium ion storage. So there's an urgent need to develop a chlorine-free simple salt electrolyte. And we also work in this direction and develop the electrolyte of such kind. And here is the structure of this this electrolyte. So basically, we have a large anion, and which contains a boron center and this fluorinated alcohol ligand, and this makes a weak coordination between the anion and the cations, and also this means we have better dissociation and higher ionic conductivity in the electrolyte solution. So from the CV, we see we have even higher oxidation stability of up to 4.5 volts against platinum, and we have very efficient magnesium stripping and plating as shown in the reduction and oxidation peaks. So the long-term cycling is also good. In a symmetric cell, we could run it for more than 1,000 cycles, and we didn't observe like obvious increase of this plating stripping over potentials. So with a nice electrolyte solution, we move one step forward. So we checking the compatibility between the electrolyte with different cathodes, just to check whether it is just as we expected. The first electrode or the cathode we tried is the benchmark cathode, the Shepherd phase. And what I want to mention here is the combination between the Shepherd phase with a chlorine-free electrolyte system is not straightforward because as reported previously, the chlorine ion has the let's say, a decisive role on this charge transfer at the interface of both the anode side and also the cathode side. So we know that the chlorine ion has a strong affinity to the magnesium, and this will, of course, change the coordination environment of magnesium in a solution. Also, that tends to form the adsorption layer, as Doron mentioned before. So this is kind of protecting the magnesium so that we could, on the one hand, have an efficient plating and stripping, and also ensures a prolonged cycle life. And at the cathode side, we also, the chlorine has could reduce the activation energy for magnesium insertion by changing the solvation, and also the Schaeffer phase, the surface molybdenum atoms has certain catalytic effect for this dissociation between magnesium and chlorine. So this further improves the insertion kinetics. And so there's no doubt that the combination between the Schaeffer phase with chlorine-based electrolyte is successful, but the multifunction of chlorine also makes difficult if we want to replace it with a chlorine-free electrolyte system. And but the case is that we tried it, and the compatibility between our borate electrolyte and the Schaeffer phase is quite good. So as shown in the charge and discharge curve here, we have a nice plateau and also a good capacity and low overpotentials after the first few cycles. The initial low capacity is related to the activation process at the magnesium side. So we also observe the similar phenomenon or activation process in the magnesium symmetric cell by using this borate electrolyte. And here, just to in order to deal with this problem, we also try to introduce additive amount of magnesium borohydride to the system, just hoping that it could somehow clean the magnesium surface. And the cell indeed shows a good capacity and also distinct voltage plateaus, even in the first cycle and onwards. So this means it works. Also, the long-term cycling at different current rates, we see that the cell could be cycled for more than 300 cycles. And this also means that magnesium boron hydride, with trace amount of this magnesium borohydride, will not affect on the long-term cycling. And this is also something I want to mention. So with the kind of successful compatibility test, we also tried with another cathode which has a higher capacity and also has a higher voltage. So here I want to present it's like this polymer cathode, the polyanthraquinone structure. So basically the charge storage mechanism of this pack material relies on the redox of these carbonyl groups. And if we consider both carbonyl groups involved in the reaction, we have a theoretic capacity of 260. But in the practical case, as reported previously, the accessible capacity is only around 110. So which is only like less than half of the theoretic value. On the other hand, we also noticed that they have used the graphite as the current collector. The reason is quite simple. Graphite is more anti-corrosive than the normal aluminum foil. So we also did a comparison study by using the chlorine-based electrolyte coupled with this PEG cathode, but we have used this carbon-coated aluminum as a current collector. As shown here, the cell could only be charged and discharged for a couple of cycles and then ends up with a very long overcharging, which indicates some corrosion happening. So the corrosion can be somehow mitigated by using a chlorine-free electrolyte system, but we also noticed that the low capacity might be from the cathode formulation. So because we know that in principle the polymer material has a relatively low conductivity, and if with the normal preparation method, we could only have very limited accessibility of this active material from the anode. That's why here we have used a reprecipitate method, that we're hoping to have homogeneous loading of the active material on a carbon matrix, which has a high surface area, so that we could have increased conductivity of the cathode and also have more contact with electrolyte. So we hope by this approach we could increase the capacity as well. So here I show you some typical electronic microscopy images, and basically we see that so the first column is the pure carbon matrix, while the second column is the carbon with the active material loading. So we see the amorphous region, which was marked by these original orange colors. They are like dispersed well on the carbon matrix. So then we tested the battery performance using this new cathode design and also coupled with the borate electrolyte. And here we see basically we could run a cell for up to 500 cycles with the normal or let's say standard cell components, which indicate a good compatibility. Also, here we could achieve high capacity with the new cathode formulation, and this is close or even exceed the theoretic capacity a bit. And with the homogeneous distribution of the active material on the conductive carbon, we could also achieve fast kinetics, as demonstrated here in the CV with different scan rates. So the next material I want to show you is the vanadium tetrasulfide, which I have presented yesterday. So I don't go to too much detail here. I only just want to highlight that previously there's also a report about this VS4 cathode, but they could only achieve a capacity of, let's say, less than 150 milliampere hour per gram, and this is still with less than 1 electron transfer per VS4 structure. But if we switch to this borate electrolyte, we have much improved capacity, and also we have a very nice platoons. And the reason, or a possible reason, could be that the sulfur dimer we have in this VS4 structure, they are quite sensitive to the nucleophilic species. So if it's coupled with the APC electrolyte, then we have the breaking of the sulfur-sulfur bond, so that of course we have a relatively lower capacity. And the last example is, or the compatibility test is with the high capacity sulfur cathode. So in this section, we have investigated the sulfur redox by using this borate electrolyte, and we use the operando Raman technology, and also to correlate the Raman modes with different polysulfide species with the help of DFT calculation. And this result in these two graphs. So basically we have the change of different polysulfide, or let's say polysulfide species evolution during charge and discharge process. And in principle, we have like a reversible conversion from elemental sulfur through this long chain and short chain polysulfide intermediate species, and ends up with the magnesium sulfur at lower voltages. And so this reaction mechanism is quite similar as what we have investigated before by using the chlorine-based electrolyte. So this also means that our electrolyte is compatible with the sulfur cathode. To sum up, I would say that the chlorine-based electrolyte are still prevalent electrolyte for magnesium batteries. So the fact is that the chlorine has multifunctions in the magnesium or let's say enable magnesium plating and also insertion, de-insertion. Now it's still difficult to find, or there's no report about some additives that can replace the chlorine ions. But we should also realize that the corrosion issue is really the big problem, especially if we want to scale up the system and in the manufacturing, for example, this will bring or a lot of problem and needs more efforts. As reported yesterday or presented yesterday by Justin, they are trying to find out some alternatives for this chlorine species, but from our side, we believe that the chlorine-free electrolyte system is a more straightforward solution and is practically more feasible for this processing and manufacturing, which makes the easy transfer of the knowledge or the technology. Also, the sample sort system offers more possibility to just to tune the electrolyte solution without much concern about this complex equilibrium. This is very important for the sulfur battery and also for the organic battery, I think. We know that even in case of lithium sulfur battery, we have to rely heavily on the additive, this lithium nitrate. But in case of magnesium sulfur system, we are still looking for a proper additive that could at least extend or prolong the cycling with the sulfur cathode. But I mean, the chlorine-free, the sample salt electrolyte system is definitely a good benchmark. So from where we could further develop or just to tune the electrolytic property and this compatibility with different cathode materials. As I have presented today, the magnesium borate electrolyte has good electrolytic properties and can be applied to various cathode systems. In the next step, we are trying to just to check the compatibility or the magnesium insertion to high voltage cathode materials, because the advantage of the electrolyte system is also like they could provide a large electrochemical window. And also we are persuading a high energy system. Also, we hope that the long-term cyclic stability in the symmetric cell could also be transferred to this full cell system in the future, hopefully. And then at last, I would like to acknowledge the financial source, especially from eMagic project and also from this Polis and Maximar. And also the slides, we have the main contributors from Zhenyou Zhaokager and also Vinaya and Yanlei, and also the firmness support from Krishna. And with that, I would like to thank you for your attention.
Thank you for your nice talk and contribution. Just one question. Afterward, you can follow the another question by the Q&A chat. Yeah, you want to reply. Just one question having here from Nekjung Dan Thing. They say, thank you for the nice talk. Why do some no chloride DME based electrolyte has anodic stability, probably far above anodic stability of the solvent like DME? For example, 4.5 volts versus magnesium for a magnesium borate electrolyte in DME.
This is a good question. I think this is also like the research topic, or the presentation what has been shown yesterday. So where they did this.
This is because of absorption phenomena.
Sorry?
No, this is because of absorption phenomena. You have absorption phenomena that extend the electrochemical window. It's it's a metastability is reached by absorption phenomena. It relates to the absorption of the anion on the electrode.
Yeah. And also, I think there will be some kind of some layer formation on the anode side, or some let's say let's say in case of the lithium ion batteries, we also have this problem, but in that case we have some oxidation of this aluminum foil, where we could have like a extended operating window, electrochemical window. Yeah.
So thank you, Zhenyou. Please look at the question that you have in the chat, in the Q&A chat. Just follow your reply to the attendance. Thank you. Let's introduce to the next speaker.